Magnetic flux density is defined as follows. Magnetic flux density at a point in space is the force experienced per unit length by a long straight conductor carrying unit current and placed at right angle to the field at that point. So we can write F is equal to ILB and B is equal to F upon IL. From this we can derive the unit for magnetic flux. It will actually be Tesla. 1 Tesla will be equal to 1 Newton per ampere meter. Let's solve some of these questions. A current of 0.2 ampere flows in a wire of length 2.5 meter placed at right angles to a magnetic field of flux density 0.6 T. Calculate the force on the wire. For formula, we have F is equal to ILB. For perpendicular, for right angle, we will examine sine theta because sine 90 is equal to 1. So force equal to just multiply these quantities 0.20 into 2.50 into 0.6. By multiplying these quantities, you will get the force. For question number 6, it says a 20 centimeter length of wire is placed at a right angle to a magnetic field. When current of 1.5 ampere flows in the wire, a force of 0.015 Newton acts on it. Determine the flux density of the field. So this will be 0.2 meters. We will simply put the values of all of these quantities and we will get our answer. The next question says a wire of length 50 centimeter carrying a current lies at right angle to a magnetic field of flux density 5 millitesla. This will equal to 0.5 meters, and also the Tesla will be equal to 5 into 10 power minus 3 Tesla. Part A says if 10 power 18 electrons pass a point in the wire each second, what is the current flowing? So we will use the formula I is equal to Q upon T, which is equal to NE upon T. And we have been given some values here. N is equal to 10 power 18. And E has been given here. It is 1.6 into 10 power minus 19. And this will all be per second, so it will be upon 1. So by simplifying this, we will get the answer 1.6 into 10 power 18 minus 19 amperes. It will be 1.6 into 10 power minus 1. So this will be current. We also have to calculate the force. So we will use the SEM formula. F is equal to ILB. And by putting the values, we just found I. Length is given by 0.5 meters. And B is equal to 5 into 10 power minus 3 Tesla. We multiply all three of these to obtain our answer. Let's discuss another topic, which is current crossing magnetic field. When we place a coil in a magnetic field, it will start rotating. Now we'll study about the magnetic field's direction. This is a magnetic field, and we have placed a coil which carries current. On left, the direction is downward. On right, the direction is upward. On top, the direction is opposite to the magnetic field. And on the bottom, the direction is parallel to the magnetic field. The formula we use is F equals to I into L cross B. And as we discussed earlier, F is equal to ILB sine theta. Here, theta can be 0 or 90, as it is parallel or anti-parallel. In both of these cases, the force will be 0, because sine 0 and 90 both are equal to 0. The force will only act on the perpendicular side, which are the left and the right side. I made a mistake here. This is not 90 degree, it is 180 degrees, because both of these are parallel. To calculate the direction of the force, we will use right hand rule. We will apply it on the left side. This is the first vector. This is the second vector. Place your hand in the direction of the first vector and curl your fingers in the direction of the second vector. We will get the force, which will be out of the page, which is shown by a dot, and on the opposite side it will be into the page, which is shown by a cross. As the force is opposite on both sides, the coil will start rotating. This is the basic principle that is used in motors. Also now, torque is produced. So when a coil is placed in a magnetic field, torque is produced. This is also an effect of the magnetic field. Question number 10 says a wire of length 50 centimeters carrying a current of 2.4 amperes lies at a right angle to the magnetic field of flux density 5.0 millitesla. Calculate the force on the wire. So the length is 0.5 meters, current is 2.4 amperes, and flux is 5 into 10 power minus 3 Tesla. Find the force, which will be equal to ILB. So we will just multiply all three of these values. Our result will be in newtons. The coil of an electric motor is made up of 200 turns of wire carrying current 1 ampere. The coil is square with both sides length 20 centimeter and it is placed in a magnetic flux density of 0.05 Tesla. Part A says determine the maximum force exerted on the side of the coil. So force, we will use the same formula, F is equal to ILB. And as it is placed perpendicular, so there will be no sine theta, just multiply it by n. ILB is for one conductor, and if we have a number of turns, like here we have 200 number of turns, so we will multiply by n. Just multiply all of these quantities and we will get the force. Part B says in which position must the coil be for this force to have the greatest turning effect. So the answer to this is that if the coil is placed perpendicular to the magnetic field, then there will be maximum force or maximum turning effect. And in case of parallel, it will be 0. Part C says list 4 ways in which motor could be made more powerful, that is, have greater torque. So the 4 ways are increasing the number of turns, increasing current. Length cannot be increased as it will make it heavier, but it can be increased to some extent. So that's the third way, and fourth way is to increase magnetic field. Length and area are similar quantities as they will both increase area, so they can be used interchangeably. So the 4 ways are magnetic field, area, number of turns, and current.